and some randomness. So what it means to be random, how we can use randomness to run simulations that we may not be able to perform in real world situations. So this is going to be kind of where we're going here. So first thing, when we talk about random, a random phenomenon is any situation in which we know what outcomes could happen, but we don't know exactly which outcome will happen at any given time. Can anybody think of an example in the real world where you know what possibilities there are that could happen, but you don't know what's going to come up when you perform that particular flipping a coin? If you were to flip a coin, do you know what can happen? Do you know what your options are when you flip a coin? Yeah, it's either going to be heads or tails, right? But every time you flip, do you know what's going to come up? No, not unless it's a weighted coin that you know goes to one side or the other. So we got flipping a coin, and the others?
Lottery.
The lottery. Rolling the dice. Okay, so anything that we know what can happen, but we don't know what's going to happen, that's a random phenomenon. So the two examples I usually talk about, you guys already talked about. Flipping a coin, rolling dice. Okay, so when you roll a die, you know it can be anything from 1 to 6, but you don't know what it's going to be every time you roll it. So that's what we talk about when we mean random. All right. Now, with randomness, we talk about this idea of the law of large numbers. This is an extremely important concept here, one that you guys definitely need to understand. You need to know how to use it and what it actually means. So the law of large numbers says, in the long run, the frequency of outcomes for a random phenomenon will begin to approach a single value. So if we were to perform a random phenomenon over and over and over and over again, we should start to see a leveling out. We should start seeing things start to come together towards a certain value. For instance, when you flip a coin, what's the probability that it comes up heads? 50%. And why do you know that? Okay, there's two sides. We know that it should come up evenly overall. Now, does that mean if I flip a coin 10 times, I'm going to get exactly 5 heads and 5 tails? No, it doesn't. But we know that on each of our flips, we should have a 50% chance. That's kind of what we're dealing with here. So this law of large numbers, what it does is it allows us to talk about the probability of a specific event. So what happens with this law of large numbers, when I start flipping a coin, okay, so if I'm looking at flipping a coin, if I look at the number of heads that come up, so in this graphic, we're looking at the proportion of heads. So the first time they flipped, they got 1 head, so 100% heads. The next time they flipped must have been a tail, so they got 50%, 1 head, 1 tail. And then they kept flipping. And as they flipped every time, they calculated the new proportion. How many heads compared to how many tails popped up each time. Okay? Now when you notice, in the short run, in like 5 flips, 10 flips, even up to 50 flips, what's happening to the number of, or the proportion of heads that we get? Yeah, it's starting to kind of get, so it starts off very sporadic. We're jumping all over the place initially, but then as we increase the number of times we run it, what's happening? It's starting to level off. It's starting to get closer and closer to that 50-50 split that we would expect. Okay? So with the law of large numbers, basically what we're talking about there is if we perform a random phenomenon in the long run, in an infinite number of trials, we should start to see everything that we expect even out in the end. So we should start to see about 50-50 split between heads and tails if we were to do it over and over forever. Does that kind of make sense? Okay? So that's what that law of large numbers says. Now, the idea of probability, so what we talk about when we talk about probability is that randomness is predictable in the long run. If we were to flip a coin forever, over and over, we should end up with an exact 50-50 split between heads and tails. If we roll a die forever, over and over, in the end, we should have the same number of ones, same number of twos, same number of threes, and so on up to 6. So it should evenly distribute itself out. So that's what this idea of probability is. Now, we use probabilities to calculate in the short run as well. So if I were to roll a die, what is the probability that I roll a 3? Yeah, 1 out of 6, or about 17%, 16.7%. Okay? So we can use it, but what we're talking about with probability is the long run. All right? Now, our intuition tells us random phenomena should be predictable in the short run, but that is not the case. So what a lot of people do is they misunderstand this idea of the law of large numbers. We know that in the long run, we should get a 50-50 split between heads and tails. But what people assume then is that if we were to look at an event where we actually flip a coin 10 times, we assume we should get 5 and 5. And that's not the case. It's a completely random event, which means we don't know what's going to pop up at any given time. So what people try to do is take that long run frequency and apply it to short run models. So think about this example right here. I'm going to toss a coin 6 times and record heads or tails on each toss. So every time I flip the coin, I record exactly what came up. Now, which of the following outcomes is more probable? So which one's more likely to have occurred? So I tossed my 6 coins. I got heads, tails, heads, tails, tails, heads. I did 6 times. I got tails, 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 heads, heads, heads. Okay, so if we look at these two, what people want to do when they look at these two is say that this one is more likely. Why do you suppose they do that? Because it goes back and forth more. People don't like the idea that random can be the same thing over and over and over again. Okay, when you flip a coin, you do have a possibility of flipping tails any number of times in a row, or flipping heads any number of times in a row, because it's completely random. We don't know what's going to pop up. So when we look at these events, people sometimes trick themselves into believing one thing is more likely than another. People like to think this is more likely because it looks more random. Okay, but the thing about random is it doesn't have a certain look. It can be anything. So when we look, both are equally likely. Heads and tails should show up equally within a long sequence of tosses. But there's no predetermined order in which they must show up. So we don't have to have an equal split at every step of the way. So with this, since we had 3 heads and 3 tails in our 6 tosses, we can say that those probabilities are identical. Okay? So the coin has no memory, which means it doesn't know what outcomes or what past outcomes happened. So it means it can't try to create a balanced sequence. That coin has no effect on what comes up when. So that's what we talk about when we talk random events. So random phenomenon and this long run that we're trying to get across here. Okay? Now, same thing. People misunderstand this idea of a long run. When we say in the long run, we should get a 50-50 split on heads or tails. Or in the long run, we should have an exact even distribution of numbers when we roll a die. So people assume that after a long run of some certain event, if an outcome hasn't occurred, it's due to happen. Have you guys ever heard that phrase, I'm due to have this? Where do you normally hear it? In sports, you hear it a lot, right? A hitter hasn't had a hit in 10 at-bats, and so they say, he's due to have a hit now, right? Or you have weather. We haven't had rain in 35 days. We're due to have a day with rain. Things of that nature. So what people are doing here is they're trying to take this long run idea and they're trying to condense it down into short-term probabilities, and that's not the way it works. Just because something hasn't popped up in a while doesn't mean it's any more likely to have occur next in the long run. Okay? So, this idea is called the law of averages. It doesn't exist. When that hitter comes up to the plate, even if he hasn't hit in 20 at-bats, he is no more likely to get a hit at this at-bat than he was in any of the previous 20. Okay? If we're talking weather, just because we haven't had rain, or just because last month or last year we had a warmer winter, doesn't mean that we're due a cold winter the next time. Okay? It doesn't matter what's happened in the past, it's only going to be what happens on the next try. That's what the whole idea of randomness is. So the cartoon here, we know you haven't had an accident in 15 years, that's why we're raising your rate, because you're due to have one. Okay, so they're using that law of averages to try to increase rates on their insurance there. So the law of averages doesn't work. When people use that term, another place people tend to use this law of averages is in gambling. If they're looking at like the roulette wheel, if a red comes up over and over and over and over, some bettors bet big on black for the next one because they assume it's due to happen next. And that's not the case. Each time they spin the ball, it has the same likelihood of landing in red or black or green each time. So you got to make sure that you kind of condition yourselves to get away from this idea of the long run. When we say long run, we mean an infinitely long run. If we were to do it forever, then we would see this pattern emerge in the end. But in the short run, we only know in theory what should be coming up next. Does that kind of make sense? Okay. So, let's get to simulations. Oh, one thing I want to talk about randomness. I don't know if you guys caught this on the video yesterday. But one of the things about randomness that they brought up, did any of you guys have, so you guys have iPods, or you listen to music on the phone, or you have some type of MP3 player, right? And they all have a mode that's a shuffle mode, correct? Now when you say shuffle, what do you guys expect to have happen? Random songs, right? Now, when Apple first created the iPod, the very first generation iPod, they had a system in place that took every song within your library and truly randomly distributed it. So when you were actually playing your shuffle, your songs were truly coming up randomly. Now what happened with that is that since every single song has the same probability of coming up every single time, what people noticed was they'd either get songs that come back to back. So you listen to the song and then that same song comes on right away after. Or they might have that song and then a couple songs later it comes back up. And people didn't like that. When they said shuffle and it said random, they thought that meant every time they'd get a new song, right? So after that first generation, iPod had to change things up. So they built in a system that was no longer random. It made sure that once a song was played, it couldn't come back up for a certain number of, or a certain time. So when you are looking at that shuffle, what you're assuming is random is not random at all because they've had to program it to go against randomness. Does that make sense? So that was something else I wanted to kind of talk about. When we talk random, it doesn't mean that each time something different is going to happen. It means that we don't know what's going to happen. We only know the possibilities. Okay? Now, simulations. Simulations are very important for modeling real-world situations. So there are times where we may want to find out what will happen given a certain scenario. And we don't want to spend the time or we don't want to spend the money going through a process of collecting real-world data. So if it's something that can be modeled with random digits, something that we know is a random phenomenon, something that we know is equally likely to occur, we can use simulations to run things much quicker and much cheaper. Okay? So we're going to be modeling real-world situations using random digit outcomes. That's why I gave you guys your table Bs for today, because we're going to do an example here where we use some random digits to model. So in a simulation, we're going to be running trials. Trials are a sequence of events that need to be investigated. So a trial is going to be a sequence of events that needs to be investigated. So some of the trials will run. We continue a trial until a certain point has been reached, until we hit a certain criteria. Other times, a trial may be a set number of random digits. We might want the first 10 digits, that's trial 1. The next 10 digits, that's trial 2, and so on. So the trials can change based on the scenario, and we'll talk about that with some examples here. Now, when you run a simulation, you want to make sure that you run lots and lots of trials. Remember, the whole idea here is the long run. If you only run 1 or 2 trials for a random event, you're not going to necessarily be getting very accurate information. So in most cases, if you're going to run a simulation, the reason we're running the simulations is that they're much faster, much cheaper than the real-world alternative. So you should be able to run lots and lots of them fairly quickly. Now, as far as we're concerned in class, it's like for the homework, for tests, quizzes, things like that, we only have a certain amount of time to work with. So most of the time when we run our simulations, we'll only stick to like maybe 5 to 20, depending on how quick the simulation is. So that's good for at least getting an idea of what we're looking at, but if you were going to run a real-world simulation, you would need to do hundreds or thousands of simulations to get an accurate description of what's going on. Okay? Now, as you progress through your simulation, you need to keep a record for each trial. You need to figure out, okay, what was I trying to measure? What was my response variable? And what was that with trial 1? Record it. What was that for trial 2? And record it. And so each trial you run, you have to keep record of what actually occurred in your simulation. Okay? So, to build a simulation, we're just going to kind of go through the steps, and then we'll go through an example so you can kind of see how these all come out to work here. First thing, in any simulation, the first thing you need to be able to do is identify the components to be repeated. So this is your random phenomenon that you're going to do over and over and over again. So if I wanted to test the fairness of a coin, let's say you and your friend have been doing this thing where you flip a coin to see who goes and does whatever, or who buys lunch, whatever it may be, and you've had to buy lunch the last 25 times. Okay, you might start to suspect that the coin is weighted. So if you wanted to, you could sit there and flip it over and over and over, run a series of trials. That would be your component. You're flipping the coin, and you'd run a certain number of trials to figure out if the coin appears to be weighted or not. Okay, so something like that. So the component, what are you going to be doing over and over and over? What random event are you going to be applying each time? The next thing you need to be able to do is determine how you are going to model the component's outcome. So how are you going to label the different outcomes using random digits? So maybe you want to use the digits 0 through 9, and you split them up in a certain manner and give this event a set of numbers, this event another set of numbers, and this event another. Maybe you need to go from 00 to 99, or 001 to 100, whatever it might be. So you're going to try to label your components, the different outcomes that could happen, so that each number represents a specific outcome of your particular random event. So when we're determining the component's outcome, you're trying to model it, you're trying to label, so that each number represents something in the real world. Then you're going to actually start running your trials. So once you know what your component is, you know how or what each number represents in the real world, you start generating those random numbers and recording what's happening. So then you start applying these to your trials. Once you start running your trials, again, point of emphasis, make sure you run a lot of trials. So run enough so that you can get the most accurate description of what's going to happen with this random phenomenon. At the end of each trial, make sure you collect the information, collect and analyze the results. Look at your response variable. What are you trying to measure overall? So make sure you're keeping track of everything as you go throughout each trial so that at the end you can bring it all together and figure out what value your particular response variable takes on. Okay? So, let's do an example. A cereal company put trading cards of athletes in their boxes to boost sales. 20% of the boxes have Tiger Woods, 30% have David Beckham, and the rest have Serena Williams. How many boxes do we expect to buy in order to get a complete set of cards? So we know that this cereal company has packaged cards within their cereal boxes. So 20% of the boxes should contain Tiger, 30% should have David Beckham, and the rest should have Serena Williams. Now, can you imagine running this type of simulation with real-world information? What would we have to do? We'd have to buy cereal over and over and over again, right? So we'd have to continue to buy boxes over and over and over again until we get all 3 cards. Then we'd have to go back and buy box after box after box until we get 3 cards. And then we'd have to go back and buy box after box after box until we get 3 cards. So in a real-world scenario, this would cost us a lot of money, and it would take a lot of time. Okay? So instead of running it in a real-world scenario, we can take the information given and run a simulation. We can use random digits to denote a Tiger Woods card, and random digits to denote Serena Williams and David Beckham. And so then all we're doing is looking through a list of numbers on a table or having our calculator generate a bunch of random numbers for us, and that will give us a look at what the real world would happen, or what would happen in the real world. Okay? So, since we know 20% of all the boxes have Tiger Woods, 30% have David Beckham, and the rest have Serena Williams, every time I open a box, I know I have a 20% chance that Tiger Woods is in there, or I have a 30% chance that David Beckham is in there, or a 50% chance that Serena Williams is in there. Everyone okay with that idea? So because those equally likely outcomes are occurring here, we can simulate this using our random digits. So the first thing we need to do if we want to run a simulation, we need to determine what our component is. So what are our components going to be? What are we going to be doing over and over and over again? We'd be buying cereal and opening the box, right? So we're opening the box of cereal to figure out what card is in there. So our component is going to be opening the box of cereal and getting a trading card. We're going to do that over and over and over again, but we don't want to spend the money doing this in the real world, so we're going to do it using random digits. So once we know what we're doing over and over and over again, we need to figure out how we want to assign digits to our components here. How are we going to decide what numbers represent what? So our next step, determine how to model. So I know 20% of boxes should have Tiger Woods. I know 30% of boxes should have David Beckham. I know 50% of boxes should have Serena Williams. How could I use that information to assign numbers to represent getting a Tiger Woods card, and then different numbers to represent David Beckham, and different numbers to represent Serena Williams?
Tiger Woods gets 2. The first 2 numbers, David Beckham gets the next 3, and then Serena gets the last 5.
All right, take 10 digits. So if we have 10 digits, let's say 0 to 9, right? If I make 2 of those digits represent Tiger Woods, that means if I'm randomly generating numbers, I have a 20% chance of getting those 2 digits, right? And then if I make 3 of those digits David Beckham, then as I generate random numbers, I have a 30% chance at any given time that that number comes up. And then the last 5 numbers will go for Serena Williams because they have a 50% chance of coming up. So what we're going to do here is we're going to let 0 through 9 represent the cards. So we need to give 2 of those numbers to Tiger Woods. So the easiest thing is just give them 0 and 1. So anytime a 0 or 1 pops up, that's a Tiger Woods card. 2, 3, and 4 will represent David Beckham, and then the rest, 5 through 9, will represent Serena Williams. Now, could I have just as easily said 6 and 7 will represent Tiger Woods, 8, 9, and 5 will represent David Beckham, and then the rest are Serena Williams. Yeah, it doesn't matter how I assign it as long as Tiger has a 20% chance of coming up, David Beckham has a 30% chance, and Serena Williams has a 50% chance. For that matter, I could have just as easily said, go from 0, 0 to 99. So 0, 0 to 19 would give me my first 20 numbers. That would be Tiger Woods. 20 to 49 would be David Beckham. And then 50 to 99 would be Serena Williams. So I could have used 2 digits. Now, why would I choose to use 1 digit at a time as opposed to 2 in this scenario? All right, because if we're looking at a table of random digits, what's easier to find, 1 digit at a time or 2? 1 digit at a time is easier to get, right? So if we can simplify it down to 1 digit, we want to do that. If we can't, then we have to use 2 digits or 3 or whatever else we need, right? Since these were all very nice even percentages, that's another thing that helps us use 1 digit at a time. If they had done something like 23% of boxes were Tiger Woods and 37% were David Beckham, could we split it with 0 through 9? No, because with 0 through 9, there's no way to get exactly 23% or 37%. So there we'd have to expand to 100 digits, make 23 of them, Tiger Woods, make 37 of them, David Beckham. Does that kind of make sense? So what you need to do with this part, and this is the part that generally screws people up, is assigning the numbers for their components. What you have to think about is think about a range of numbers where you can assign the same percentage of numbers to each of your categories. They'll tell you how often something should pop up. So you just need to make sure that the numbers you pick represent the same percentage as the real world scenario. Everyone okay with that? So here's how we're going to distribute our values then. 0, 1 Tiger, 2, 3, 4, David Beckham, 5 through 9, Serena Williams. So now we have to actually run our trials. Okay, we know what we're going to be doing over and over. We know how we're going to run it over and over. Okay? So we need to start generating random digits to represent opening boxes, and then we continue until all trading cards are found. Okay? So we're going to go ahead and run 5 trials here. Okay? So what is our response variable? What are we looking for overall? The number of boxes we should expect to buy before we find all 3 trading cards, right? So we're looking for how many boxes we would need. So here, we're looking at what boxes or what cards come up, right? But what we want to measure is the number of boxes it took us to get what we want. So we have the trial number, we have the cards that we're going to generate here, and then how many boxes did we have to open before we found all 3 cards. So if I'm going to run my trial, I need my table of random digits. We're just going to use that for now because it's easier. You can just as easily use your calculator to generate random digits as well. It'll do the same thing, okay? But we're going to use table to keep things consistent. So someone give me a line to start at.
102.
102. So everyone get to line 102. So what you're going to do is, starting at line 102, you're going to choose the very first digit in that line, which is what? 7. What does a 7 represent? Serena. So there's a Serena card, first box. So as you're going through this, you'll want to make sure you know what each of these digits represents as they come up. So a 7 means we got a Serena Williams card. What's the very next digit? 3. What did 3 represent? Beckham. So Beckham was 2, 3, and 4, right? So there's Beckham. What's the very next digit? 6, which was a Serena, so we don't need that. 7 again. Now, can I have repeats here?
Yeah.
Yes, before when we sampled, we were pulling people physically out of the pool as we were picking them, right? So if I had a 7 to start with, I couldn't get a 7 again because I'd already pulled that person out. But in this case, repeats are acceptable because it just means another Serena card came up. If we were to eliminate repeats, we'd be changing the probability of getting Serena every time we drew a number. Okay? So 7 again is okay. So what's the next one after that?
6.
6. And then
4.
4, and then
7.
and then
1.
and now 1 is a Tiger Woods card, right? So for that one trial, because that's the end of the trial, we now have Serena, Beckham, and Tiger. So for that trial, how many boxes would we have had to bought before we got all 3? So for trial number 1, 8 boxes was what it took to get all 3 cards. Now, picking up exactly where we left off. So our next trial picks up exactly where we left off. So after that 1, what's the next digit?
5.
5, which is Serena. Then
0.
0, which is Tiger. And then
9.
Serena again.
9.
Serena again.
4.
That's Beckham, right?
Yep.
So there's Beckham. There's all 3 cards, so we can stop that trial. So this time it only took us 5 boxes. And now picking up where we left off, continue on. What's the next?
0.
0. Then
0.
0.
1.
Keep going.
9. 2.
Okay. So we have 3 zeros, 1, 9, 2. So there's Tiger, Serena, Beckham. We got all 3 now. So that took us 6 boxes. Okay, continue on.
7.
7, Serena.
2.
2, which is Beckham.
7.
Keep going. 7 again.
Yep. 5. 4. 4. 2. 6. 4. 8. 8. 2. 4. 2. 5. 3. 6. 2. 9. 0.
All right. So on that particular stretch, we would have had to buy 21 boxes of cereal to get all 3 cards. All right? So that time it would have taken us a lot of boxes to get our 3 cards. So if we were looking for a Tiger Woods card, we would have been in a lot of trouble there money-wise. Okay? So now, picking up where we left off, let's do one more trial.
4.
4.
5. 4. 6. 7. 7. 1.
Okay? So that time it only took us 7 boxes, right? Okay? So, we wanted to know how many boxes we should expect to open before we find a Tiger Woods card. So we ran 5 different trials. So trial 1 took us 8, trial 2 took us 5, 3 took us 6, 4 took us 21, 5 took us 7. So if I wanted to know overall how many boxes I should expect to open, what would I want to do with all those totals there? Add them up and average them, divide by 5. So if I add all these up, you get 47, right? And 47 divided by 5? About 9.4. Okay? So, what this tells us is, on average, based on our simulations, so that's a key here, based on our simulations, on average, you could expect to open 9.4 boxes of cereal before you receive all 3 of the different trading cards. Okay? So that's what simulations do for us. They allow us to take a real-world situation. So notice, if we wanted to run even just 5 trials, we would have had to buy 47 different boxes of cereal for those 5 trials. And 5 trials is not generally enough to actually draw a decent conclusion. When we run a process like this, we expect hundreds or thousands of trials. So think about how much money that would cost to run this over and over and over again if we did it real world. So that's where the simulations come in. Save us time, save us money. Does that make sense? And you can also see why, as far as homework, tests, and quizzes go, we try to keep these as short as possible as far as number of trials, because they can take a little while to do. Okay? So, we took our components, analyzed our response variable. That's what we just did there. So we counted up the number of boxes it takes to get all 3. So we added them all together, averaged, and then we drew our conclusion based off of that average. Everyone okay with that? Now, some similarities between this and random sampling. If I had each of you run your own 5-trial experiment, and you got to pick where you started in the table, would you all get the same value at the end? No, you'd all get different values, which means if we took all your different values and put them together, we should get a value that's closer to the true. We should get a more accurate picture of what we should expect overall. So with only 5 trials, it's not too likely that this is going to be very accurate. We didn't run it a lot to figure out exactly how many boxes we should have, right? Especially since one of the trials took way, way longer than any of the others. So we would want to keep running these until we got it narrowed down to a more consistent value. Okay? That's it. So, you got your assignment here. And then before I let you work here, I do want to talk about one other idea here. So one other way simulations can occur. So this was one where our trials consisted of picking a number over and over and over again until we hit a certain criteria. Right? So we kept running a trial until we found all 3 cards. We kept running a trial until something happened. Okay? That's one type of simulation. Another type of simulation would be where we have a fixed number of components per trial. So let's say we changed the situation here. And let's say you really wanted to find a Tiger Woods card. So the 3 people, you really wanted to make sure you had a Tiger Woods card. Okay? So if we looked at maybe we can only afford like 5 boxes. Okay, so we can afford to buy 5 boxes. I really want to make sure I get a Tiger Woods card. So we can figure out the probability. What's the likelihood that in 5 boxes you find a Tiger Woods card? Something like that. So in that case, what you'd be doing is you'd be generating 5 numbers at a time. So we would pick the first 5 random digits. Say they were 2, 5, 7, 0, and 8. Okay? So in those 5 boxes, did I manage to get a Tiger Woods card? Yes, I did. So what we'd be looking at here is, did I get a Tiger or not? Yes, I did. And then let's say in the next trial, I open 5 boxes, and let's say we get 72254. Did I get a Tiger there? No. And so I continue this process over and over. Now this time, my trials are fixed to 5 components at a time. So I'm going to analyze the first 5. It's going to be a yes or no. Did I hit what I wanted? Yes, or did I not? And so on. And so then at the end, you're going to have yeses and nos here. And if we're looking at, well, what's the probability that we find a Tiger Woods within 5 boxes of cereal? All we have to do is look at the number of yeses. So 2 total yeses out of 5 total trials. So we'd have a 40% chance. If I could only afford 5 boxes, I've got a 40% chance of getting a Tiger Woods card. So the 2 types of simulations you'll run into. The first type is like what we did the first time. That's where you have to run your trials until a certain outcome occurs. The second type is a fixed number of components per trial. So they're going to say you're going to do this event 10 times or 5 times. And then you're looking for a specific outcome. So then the answer becomes yes or no, and then you're calculating the percentage. What percent of times did you accomplish your goal? Does that make sense? All right. So the rest of the time is yours. Use it to work on the assignment here. This assignment, it's cut down from last year's, but it'll still take a little bit of time. Okay, so these problems can run a little bit longer. When you get to the simulations, so 25 and 27, they actually have you run simulations. I forgot to check on here. What I want you to do on 25 and 27, because it does not specify how many trials you're supposed to run. And so I have a certain number I want you guys to do here. Do 10 trials. So 25 and 27, do 10 trials for each of those simulations. Okay, and of all the questions, those are going to be the two that probably take the longest, just because, like you saw, as we were going through it, it can take a little bit of time to go through. So I want you to run 10 trials. Now, for those 10 trials, you can use the table of random digits. Now, the ones I gave you today, I need back, so I'll have you guys turn those in before you leave. But you have the table of random digits in your book, or if you want to take a quick picture of it with your phone and use that, you can do that. Or if you want to use your calculator. You guys know how to generate random numbers on your calculator now, yes? So all you have to do is generate your random numbers and just record as they pop up, okay? So when you run your simulations there, that's what's going to happen. Now, also keep in mind then, when you look at my answer key, if you didn't use the same line on the table of random digits that I did, are you going to get the same results as I did? No. If you use your calculator, you're probably going to be seeded to a different value, which means you're not going to get the same results I do. What you need to make sure you do when you check your simulation against mine, make sure you ran it the same way. So the process should be identical. You just might be getting different numbers. And then make sure you calculate the response variable the same. Okay, so make sure your setup, make sure your process, and make sure your calculations are all identical. But the numbers might not match depending on what you choose to start with and how you generate your numbers. Does that make sense? All right, so go ahead and get to work.